Now we're on to the dot product, the vectors chapter. Two vectors dotted into each other, and we use the little symbol, the dot. The multiplication of the magnitudes times the cosine of the angle between them. It also equals ax times bx plus ay times by plus az times bz. If you take the three axes perpendicular unit vectors, I hat, j hat, and k hat, ij and k, and you multiply them by each other, well, the angle between I hat is 0, and its unit magnitude. I hat, j hat, and k hat all have unit magnitude. So 1 times 1 times cosine of 0 is 1. The angle between j hat and I hat now is 90 degrees. Cosine of 90 is 0. I hat times j hat is 0. I hat times k hat is 0. J hat times I hat is 0. J hat is 1. J hat k hat is 0. K hat I hat is 0. K hat j hat is 0. K hat is 1. So you want to find the components of force, so applications of the dot product. Components of force along line A, and sometimes you want to do this. You have a bearing or something, and you pull on it with a certain force, and the bearing is constrained to move along a line. And so you want to know what is the force along that line. If A was absolutely perpendicular to the line, it wouldn't move. You need some component of force in the direction of the bearing's motion that would allow it to move, a collar's motion. So the force along that direction of the line is A times the cosine of the angle between them times a unit vector that represents the direction of this line. That's how much force there is in that direction. And you can get a perpendicular too. So A minus this vector here will give you the perpendicular vector. Now, we can also express A cosine theta as A vector dot UA. A vector dot UA equals A cosine theta. So now we can write the A vector as A dot UA. That gives us a scalar. The dot product gives us a scalar times the unit vector. And then we do, to get the perpendicular in the same plane as A and the force, the component along line A. So A perpendicular is be in the same plane as these two vectors. And we can just get it this way. UA equals 1. That's just another way of saying we're talking about a unit vector. We're not talking about some arbitrary vector. So here's a couple applications. I use the Excel spreadsheet again. You can use simple trig, but you can also set up an Excel spreadsheet. So here's U and V, X, Y, Z components of F, F, Y, Z components of U, F, Y, Z components of V. Find the magnitudes. That's the square root of the sum of the squares of these three components, and a unit vector in the x direction, in the force direction. It may not be needed, but with Excel it's easy to calculate. So it's information that's sitting there at your disposal to use. So we can get F dot U, which is magnitude of F times cosine theta, will give you this. And you get the dot product. This is the function in Excel that will give you the dot product right here. Sum product is the function name. You just select the three cells that represent one vector, in this case F, And the 3 cells represent the second vector, in this case, U. And there is a small error here. This would be the sum product of F times B4 colon D4, not, obviously we're not getting the same answer that we got before. So this is magnitude of F times the cosine of 45 right here. And this is magnitude of F times the cosine of 15. You get the same answer using trig. You can use trig. 100 times cosine of 45 will give you 70.7. 100 times cosine of 15 will give you 96.6. Okay. Here's a little bit tougher one. 3 dimensions. And that's why we use this. In 2 dimensions, you could probably use trig and get away with it all the time. In 3 dimensions, though, we need this formalism. Let's go back a bit. We need this formalism when we're dealing with 3 dimensions. Or at least this formalism makes 3 dimensions a heck of a lot easier. And that's what this course is all about, by the way. We're going to be studying problems, and we're going to be looking at ways to make finding good solutions to those problems easier, more convenient, shortcuts, if you will, tricks of the trade. That's what we're teaching you. We're teaching you a bag of tricks to solve these sorts of problems, the kinds of problems you will face in mechanical engineering and civil engineering. You could start with the fundamentals of Newton's 3 laws and then reinvent the wheel, what engineers have done over a few centuries, if you wanted to. Not real productive. Probably just better off learning what other engineers have done over 3 centuries. Or is it 4 centuries? It's closer to 4 centuries now. Okay, so I don't think I want to reinvent all the wheels invented in the last 4 centuries. I'd rather figure out what somebody else did and use their stuff. Okay, so now we want to know the projection of F parallel to this line AB. Here's AB, here's U sub B. I use E for the unit vector all the time, so different books write it differently. E is commonly used to mean unit vector. Unit vector along the AB direction. Same thing as U sub B, what the book calls U sub B. Get used to the fact different people use slightly different notation and connect the two. AB, we want to know the force vector here, and that'd be F dot EAB. Well, you can calculate it pretty easily. The position vector of B is going to be 2, 6, 3. 2, 6, 3. Magnitude 7. So the direction vector is going to be these 3 numbers, 0.29 or 286. We'll keep it to 3 sig figs. 0.286 I hat, 0.857 j hat, and 0.429 k hat. And we keep all digits in our intermediate calculations. And Excel will keep that in the spreadsheet. The force is 300 newtons in the j direction. And so we just dot the force, take this dot product with this. Actually, it's 300 times this number only, because these two, the zeros would give us 0 times 2 plus 0 times 3, or 0 times 0.429, plus 0 times 0.286. $257. Then you want to know the parallel component. Well, that's just this number, 257, times EAB. And here's the numbers. Sanity check, just to make sure our magnitudes are the same. F perpendicular. We get this. And that would be F minus F parallel. So 0 minus 73.5 gives us this. 300 minus 220.4 gives us this. And 0 minus 110 gives us this. Okay, that's it. That's another example of dot product. You guys work out the other examples in your textbook in the chapter. I've given you one example to show you the approach. Now it's your turn. You get to practice. Do the examples in the textbook. They will help you with your homework. And with that, that ends the video on Chapter 2 of Hibbeler about vectors.